What's the conversion? 101.8. Oh, I see. I vaguely remember this.
Give you 2 more minutes, and then I'm going to ask you to talk me through this.
We know the first two always.
Wait, can you do this? Because, one of the,
Yeah, then you can
yeah, but, wait, not the word. Oh, correct. Oh. Oh, I got 75. Wait, it's a compression, so it is negative. Oh, no, change it. Divided by what? Sounds good.
I'm still trying to find the final pressure.
Gamma's fine. Yep. I got a calculator.
Yeah. Whatever, I'll leave it like that.
Okay, 30 seconds.
It's not monotonic. It's 1.6.
Oh,
It isn't monotonic.
correct.
What?
It definitely
So
is not
gamma is
monotonic.
different.
Well, then my answer is wrong.
So gamma changes.
That's true.
So then it'd be 7/5, right? Yeah. And then so this is flipped. That's 5/7. 5/7. What'd you get for your pressure? Is that in
Liter atmosphere. Or no. Okay, I got 5.5.
atmospheres?
Okay, so
Times 3
let's
raised to
go.
5/7.
Hopefully we'll talk through the salient points. First off, again, kind of
Yeah, okay.
intuition before numbers. So is the internal energy, which remember is also directly related to temperature, going to go up or is it going to go down? It's going to go up, right? I'm compressing this ideal gas. So certainly I'm going to be using this over here. All right, so we expect U and T to increase. Okay, so how are we going to find how much it changes by? Not too difficult. Yeah.
So I guess kind of working backwards for an adiabatic process, you know that delta U is equal to
A little louder.
we know that in an adiabatic process, negative delta U is equal to delta W. Already,
Okay.
and
So there's our relationship relating internal energy and work done for an adiabatic process. Okay.
we have that equation for work, and we find PN. We have everything besides PF, which we can find using BI gamma equals PF again.
Just one more time, a little louder.
We can find that find PF using the PI to the gamma equals PF.
Yes. Okay, good. All right, fine. There's not much more to it than that. So first off, yes, we're going to use our du equals minus dw expression. Here's what we're going to use to figure out the work done. what do we know, what do we not know? We know the initial pressure, we know the initial volume, maybe there's some unit conversions, not so interested in that in class, but essential to get the right answers. You need pascals, and you need, well, in principle, you need the volume in appropriate units. So let's see, we know this drops by, let's see, it goes to 1/3 of the initial volume, so you know this. What we don't know is this, but we can find it from here. Gamma. Okay, so there's a little bit of discussion just as you were finishing up about what gamma factor we should use here. What is gamma in this case?
7/5.
7/5. Okay, so remember, gamma is Cp over Cv, a diatomic gas. Well, you might need to think a little bit about what Cv and therefore Cp are. We made some comments at the end of last Thursday, I think, about typical values of Cv for a diatomic gas. And if we're in a sort of plausible temperature range, this is going to be probably 5 halves. Cp is this plus R, or plus 1 if I'm not counting R, so it's 7 halves over 5 halves is 7/5. Okay? So 1.4 in this case. Now we've got a gamma factor, we can find the final pressure. We've got this, gamma reappears over here, we can calculate the work done, and then we just flip the sign, and that tells us how much the internal energy changes. Okay? So again, numbers not so important, but I'm just looking at my cheat sheet here. It turns out that the magnitude is about 5,000 joules for this particular set of numerical parameters for those of you who want to work it through. Joseph?
So T, so the gamma -1 is equal to a constant V over T. That is like in the ideal gas equation when you set nRT or nR constant with V, so that V1 over C1 is equal to P2.
So you can work these back and forth. It will turn out, not surprisingly, to be gamma -1 here. So maybe just take this, for example, play around with the ideal gas equation. If you like, you can do the algebra after class. You will find out that this is what you get in this case. Now, we care about this, not in this particular problem, right? Because I only know T and V. But when I do have T and V, I do need the gamma -1 factor.
So really get CP is 7 over 2, because I know that CP is V is CV plus R.
Okay, yes. So, what I should really be putting in is R's there. Okay, I just didn't put them in because I know they're going to cancel. So, to make sure everyone heard your question, where do I get CP from? Yeah?
Yeah.
Okay.
So this is.
Yeah. U of T in my notation there is simply to say that the internal energy is solely a function of temperature. That's the only state variable that it explicitly depends. Yeah.
So for adiabatic processes, are all the parameters independent of the number of moles present?
Are they independent of the number of moles present? I'm not quite sure what you mean, because of course we've still got this overall, right? So that has to apply overall. When I'm looking at pairs of variables and how they might vary in a process, then n doesn't matter. It certainly factors into this, right? Yeah.
There's a third form of the equation for work that did not involve gamma, it involved CR over R, and then it didn't involve pressure and V, but it involved the temperatures instead.
So just think about that. So the question was, you've seen a version of this that wasn't expressed in terms of P's and V's, but things like R's and T's. Where might that come from?
Yeah.
So remember, this is an ideal gas.
So the fact that PV is equal to nRT.
Right. So you may see permutations in this, okay? And depending on what your particular variable of interest is, of course, you might permute these things. But we've got PV here. Again, it's an ideal gas. Yeah. Yeah.
How do you expect us to find CV for the classes on CV?
Fair enough. How do I expect you to know CV for a diatomic gas on an exam? I will try to guide you. I mean, the reality is, it's almost always going to be 5 halves R. That's the value that pretty much holds, I think the numbers I put up on the chalkboard last week are between around 50 and 500 Kelvin. And for us, by and large, we're going to assume we're working in temperature regions that are not too far from room temperature. If it's not that, I will alert you to it, okay? Yes?
So is the gamma factor on volume only used for the pressure volume like constant, or would you ever use it for like the ideal gas equation? Because like
You will not use it for the ideal gas equation
Okay.
directly, though. But you see it appearing quite a lot. Okay, so let's turn our attention to a new topic for the last half hour. So we're going to be talking about electrostatics for the next couple of weeks. Obviously, working our way into the broader topic of electromagnetism. So I said this at the start of the semester, but just give you a quick recap. We're going to worry about electric charge for the next 3 to 4 weeks, more or less alone, both static and then somewhat in motion, when we talk about currents in practical devices. Then we're going to turn our attention to, at this point, a apparently discrete set of phenomena associated with magnetism, learn some of the basics with that, and then sort of explore some magnetic phenomena that might, again, have practical implications in terms of devices we might use. And then, of course, the end of the semester, we're going to bring these two things together because, as we know, for 150 years now, electricity and magnetism are very closely related. And just to give you a big part of the punchline away so that you can have a sense of where we're heading, magnetism is essentially a set of phenomena associated with charges in motion. Okay? So electrostatics, charges at rest, the simpler phenomena are associated with what we traditionally think of as electric fields. If those charges start moving in some way, they immediately establish magnetic phenomena. And so it's the question of motion or not, and the interesting question of relativity will fold into this at the end, or sadly not too much in the context of this course, that we can tie electricity and magnetism together in the form of electromagnetism. So, long journey, very interesting one, very beautiful one. I'm going to do a lightning, very bad pun, lightning trip through some basic electrostatic phenomena. I'm basically going to ask you to read the first few sections of chapter 21 in our textbook, which talk about simple phenomena. And then we'll fairly quickly get to talking about the intrinsic force characterization associated with electric charges, namely Coulomb's law. And we'll hopefully have time to explore that a little bit before we wrap up today. So, electricity, electric charge. Long history, discovered early on by phenomena like your experience with static electricity on cold winter's days. Phenomena are associated with what we now know as electric charges being removed in some way from materials that have overall electrical neutrality. And as you'll see, one of the sort of early conclusions you can draw from some of these phenomena is that materials, while generally being what we call electrically neutral, seem to have constituents that can be torn apart, and that whatever those constituents are have opposite characteristics in this electrical domain. So many of the phenomena are associated with things like materials. Okay. I got the right pairing here. Not so much. A little bit of activity. Let's try with this. Possible I got the wrong pairings of materials here. Look at this. Okay. Okay, now we go to it. Okay, so two materials. Importantly, in contact, probably some kind of friction forces here. Friction, as we'll learn at some point, is basically an electrical phenomenon. And apparent forces. Forces that seem to be exerted at a distance, no less. Interesting. And we start to see forces of different types. So, okay, there's a tendency for this piece of plastic now to attract with a little piece of pit that's suspended from the string. I'm actually going to let this thing touch it. That's what it just did. It was attracted and the two were momentarily in contact. Now what happens? So now it's actually pushing it away. Okay? So already some fairly interesting rich phenomena here. So that's one sort of set of early observations. That's an insulator, which means it's some type of material that doesn't have a tendency to allow whatever this electrical charge is to pass through it. This is a piece of copper metal, which, as you all know, is by contrast to a type of material that does seem to allow these electrical charges to move. And again, it seems I can exert a force at a distance on this thing by bringing whatever has happened to this in contact with it. So lots of interesting phenomena. This one's fun if it works. A little more dramatic. Let's see. So, those are some of the sort of modestly interesting phenomena. We can ratchet things up a little bit once we know more about what we're talking about with electrical charge, and we can, with modern technology, start to build up more substantial asymmetries of the electrical charge. You know what I'm about to show you now with the Van de Graaff generator. This is a device that takes those electrical charges in originally electrically neutral material, rips them apart, and puts one of them in one place and the other someplace else. And so we get a strong asymmetry of electrical charge, and in so doing, we can have much more dramatic phenomena. Let's see if I can do this. So, it doesn't seem immediately related to this, but as we're about to find out, it is. Large electrical charges, asymmetrical charges on this guy. This thing on the right is something that is electrically neutral, and whatever's going on, it seems when there's a certain threshold of asymmetry, there's a rather dramatic effect in the form of sparks of what we call electricity. Okay? Charges in motion. Looks like you can't see Joseph. Okay, I'm going to try this. It must be crazy, but here we go. Ow! Okay, so now you can see it. All right? So electrical charge. So, I'm going to be very brief on this because it's fun, but it's not particularly stuff we're learning important things about. This will start to indicate something about forces between objects that apparently share the same type of charge asymmetry. Take this away.
I want it to fly.
Not much contact.
Come on.
Okay. Try it differently. Slightly better. Find out. Rice Krispies. We love this one. Okay. So, what's it telling us? A few things we need to know. Again, you know all of this. took people a long time to figure out the bottom line, but since we know it, we're not going to spend time trying to decipher all those observations. We're going to talk about basics of this thing called electrical charge. So I'm going to ramble for 5 minutes, I mean even more than usual, and then we'll see where this takes us. So, most materials, unless we do something to them, don't have any charge asymmetry, are what we call electrically neutral. And as we learn, this means they have equal numbers of, or equal amounts would be actually a more correct thing at this point, equal amounts of what we came to call positive and negative charges. Okay, again, there's a long, rich history here. It took people a while to figure this thing out, but as we now know, materials, almost all materials, are made up of equal numbers of positive and electrical charges, aka they're electrically neutral. But if we do things, as you've just seen, in ways in which that separate those charges, we can end up with a net positive or a net negative charge, and things start to happen. So, where does it come from? Again, this took decades, hundreds of years, even more in the case of some of these basic phenomena, millennia. The origin is, of course, what we can now say in the form of atomic structure, or atomic constituents. Atoms, of course, being the sort of basic building blocks of many types. And again, with the benefit of centuries of hindsight, we know that positive charge resides typically in an atomic nucleus. Quite how, doesn't matter just yet. And negative in what we now identify as orbiting other things. Here I'm actually going to use a technical word in the form of electrons. So that's where we now understand that these charge constituents come from. So all the phenomena you've just seen have to do with situations where I'm somehow pulling these things apart, and in some cases putting excess positive or excess negative in some place and starting to see interesting phenomena. So those are some of the basic observations. It turns out, interestingly enough, that electric charge is quantized. Quantized. That means it comes in discrete chunks. It is not a continuous quantity, a continuous variable, at least down at very small scales. So that means there are chunks. And in fact, for the longest time, we thought the smallest possible amount of charge that we could ever observe was in fact precisely the amount of charge associated with the magnitude of the charge on the electron, or turns out equal and opposite, the magnitude of the charge on one of the fundamental charge constituents of the nucleus, namely the proton. So this leads us to a fundamental unit of charge, and I'm going to write it down like this. The magnitude of the fundamental unit of charge is the magnitude of the charge on an electron, simple little e. And I'm already going to kind of jump ahead and do this in a slightly backwards way, but I'm going to define a unit of charge kind of in a weird way. So we're going to quantify whatever this charge thing is in units called coulombs. As you know, most units in physics are named after prominent scientists. So this is named after Coulomb. But this is already in some weird power of 10 in terms of this fundamental charge, and it's a very small power of 10. We'll worry about that a little bit later. The definition of charge actually comes in a rather roundabout way, and it actually comes from moving charges. So I'm going to sort of sidestep that for a little while. This is at least we always thought it was a kind of smallest unit of electrical charge. For about 50 years or more, we've known that's not quite true, but it doesn't really matter for our purposes. So we're going to say that charge is quantized. And conserved, at least in some system where we can identify a boundary and we're not taking charge into or out of that system, across that boundary. So it means it can move around, there can be various balances and imbalances, but overall charge is conserved, it's quantized, so on and so forth. So we've got quantized, conserved charge, small fundamental units. It seems to come in positive and negative, what we now call them. And then in terms of some slightly higher level observation, we're working towards Coulomb's law. And weird feeling to be crunching Rice Krispies as I walk across here.
Hear it.
We've already seen there are forces associated with this. And we have seen that there are forces that seem to either attract or repel. So in a little while I'm going to start introducing some parallels with the large-scale gravitational force, Newton's law. But already there's an important difference here where we seem to see forces that are either attractive or repulsive. And again, you know most of this, so I'll be brief. It turns out the force between two charged objects is attractive between oppositely charged objects, and it is repulsive between same sign or same type charges. Okay? So again, you know most of this, and it took people a long time observing the sorts of things we were looking at to figure this stuff out. Simple now with the benefit of hindsight, but again, based on just a few phenomena, it takes some time to figure all of that out. Okay, let me just make sure I'm not missing any other key sort of phenomenological things. Probably good. I did say when I was showing you a couple of those demonstrations, these forces appear to be acting at a distance. And interesting, most of mechanics, aside from gravitation, you see that forces were all kind of contact forces in one way or another. Gravitation, of course, was one example where we saw forces acting at a distance, and this turns out